Excellent. So, hi everyone. I'm Jordan Stone, an astrophysicist at the U.S. Naval Research Lab in Washington, D.C., working with the EMPOI team. But previously, I was part of the Large Binocular Telescope Interferometer team, and I'm still involved with some instrument development projects at LBTI. So, LBTI is a unique facility, or LBT is a unique facility, and the LBTI is a unique and versatile instrument. And so LBTI was optimized for 3 to 13 micron interferometric observations, combining the light from the two 8.4 meter diameter mirrors at the LBT. And in this way, LBTI can provide resolution spanning the whole 23 meter baseline provided by the observatory. So in this block diagram, you can see the inner workings of the LBTI beam combiner. And so light comes in from each telescope from the side. Visible waves are reflected to the adaptive optics wavefront sensor for performing low background adaptive optics correction over each of the 8.4 meter mirrors. Infrared light is transmitted into the beam combiner, where there are two path length correctors capable of correcting piston and differential tip tilt at 1 kilohertz frequency. And during operations, we only use one of these path length correctors, but having both of them provides us some robustness to hardware failures. The corrected light is directed into the Knowling and Imaging cryostat, where we have two science instruments and a fringe tracker. ElmerCam is an imaging interferometer that is optimized for sensitivity at 3 to 5 microns, but can be used down to J-band. PhaseCam is the fringe tracking camera that we use that typically operates in H or K band. And NOMIC is an 8 to 13 micron Knowling and Imaging interferometer. And so exozodiacal dust was really the characterizing and better understanding the distribution of exozodiacal dust around distant stars was really the main science driver for the development of LBTI, especially the 10 micron Knoller. And we recently completed a survey of 38 stars, making 10 detections of exozodiacal dust disks. And what this plot is showing is the distribution of exozodiacal dust disks discovered by different missions. So the WISE telescope was able to discover habitable zone dust via the detection of infrared excess, but really was only sensitive to very large signals. And so the unit here is Zodi level. So that's the one Zodi corresponds to the brightness of the habitable zone dust in the solar system. So WISE was mostly sensitive to dust disks that were about 100 times brighter than the solar system. The Keck interferometer Knoller also used Knowling interferometry to tease out resolved extended signals. Its detections here are in blue. And you can really see in this plot that LBTI has provided some added sensitivity to low brightness disks that has better helped us characterize the distribution of brightnesses around nearby stars. And the big takeaway is that the typical level of dust around nearby stars is not so large as to prevent a reasonably sized aperture in space from imaging an exo-Earth in the habitable zone of a nearby star. So that's really good news and was really important work that we were able to perform with the LBTI. So here is an example of a Knowling sequence that we did with the LBT. What I'm showing here is a video of the two overlapped beams. So this is an airy ring, or sort of a diffraction limited spot from both telescopes overlapped on the gnomic detector. So the size of this is lambda over d, where d is the size of one of the apertures. And what you'll see as we scan through the delay looking for an optimal null, the starlight will blink in and out. So we're trying to find where that correct set point is to null the light. And after we find it, then we just integrate for a long time on what appears to be a blank detector, but really is a nulled starlight, where we're probing for dust emission in the vicinity of that star. And so the way that works, you can see in this plot on the left, whereas if you have a model of extended dust emission, that model gets transmitted through a sinusoidal transmission pattern projected on the sky by the nuller. And so what comes through this transmission pattern is something that looks like this down in the bottom left. And then that is convolved with the Airy pattern from the two telescopes. And so what this allows us to do is make really sensitive measurements of excess infrared emission around bright stars, because we're able to just cancel the light of the star with the nuller. So another way we use LBTI is with imaging interferometry. So these are examples of 3 to 5 micron imaging interferometry observations with ElmerCam. And what's really unique about this mode is that we're able to provide 23-meter resolution over really wide fields of view. So this is the central image is a picture of a star field in the ONC, showing 4 stars separated by more than 10 arc seconds, and we've got fringes overlapping all of them. On the left, this is an image of Jupiter's moon Io, which subtends about an arc second on the sky. And what you're seeing is the moon Europa eclipse Io. But on the face of Io, we see multiple volcanoes, and even you can tell in this image that we're resolving Loki Patera. And so over this 1 arc second face of Io, we're able to make very high spatial resolution measurements of volcanic activity. And so these data of Io were taken in M-band with an open phase loop, so without phase control. On the right is an image of, this movie shows an image of phase controlled observations. And you can kind of see the phase rocking back and forth, showing you sort of the level of the residual phase error that's coming through after fringe correction. And so Eckert Spalding has a recent paper out discussing strategies for analyzing these data for high contrast direct imaging work, and sort of addressing the unique challenges of handling this funny shaped PSF and the phase residuals. But another recent result we have with closed phase loop imaging is the detection of a companion and a bipolar outflow in the vicinity of MWC 297. So these observations were made in co-phased masking mode. And in this mode, a non-redundant mask is used over each aperture of the LBT before the beams are combined. And so you get UV coverage, including intra-aperture baselines and inter-aperture baselines. And this data set was really just a snapshot image. You can see we don't really have arcs in the UV plane. This is only about a 10-minute observation. And through the use of closure phases in this masking mode, we're really able to tolerate the 30 degrees of residual phase error that we are experiencing. So phase tracking, here's how we do phase tracking at the LBT. We create spatially modulated fringes by overlapping beams with a fixed tilt. And then we're sensitive to differential OPD by measuring the phase of those fringes, and differential tip tilt by measuring the fringe frequency and orientation. And currently we only use one output, and we're susceptible to 2 pi fringe jumps. So what's being plotted here is the null depth as a function of time. And you can see every once in a while we'll slip out of the null, and we have to manually drive the fringe tracker back into its set point. Here is sort of some plots showing our performance, our fringe tracking performance. With the phase loop closed, we get typically about 0.3 to 0.4 micron differential OPD, dominated by 50 hertz and 160 hertz vibrations. There is a vibration monitoring and feed forward system at the LBT. And on this right plot, what you can see is closed loop performance with the vibration monitoring feed forward turned off and then turned on, showing that we really do get an improvement with the vibration monitoring. So the other parameter that's important to understand for the fringe tracking is sort of what are the limiting magnitudes? What objects can we observe? And so this is a multi-dimensional question at the LBT, because you have to be bright enough in the optical for adaptive optics and bright enough in the near IR for the fringe tracker. And so this plot on the right shows optical magnitudes on the vertical axis and near IR 2 mass K on the horizontal axis. And our current adaptive optics limit is shown by this dashed orange line. So you have to be below this in order for the AO to lock on you. And our current fringe tracking limit, yeah?
2 minutes.
Okay, thank you. Our current fringe tracking limit is shown by this blue line. And so currently there is only one object in the Taurus star forming region that we could observe. And so these are just an example of targets that we might be interested in. And so we have a plan for extending the sensitivity of the fringe tracker by about 5 magnitudes. And this is going to be done by repurposing some work that's being carried out at the MMT Observatory to create a new infrared wavefront sensor for their new adaptive optics system. It uses a CellX avalanche photodiode infrared array combined with an astronomical research camera controller to provide the clocks and biases and signal processing. And so the current implementation has the preamp board is too large to fit inside the cryostat. So we need to redesign this in a way that we can get the CellX array into NIC. And there are also concerns about 10 micron glow from this preamp. So we're going to remote this preamp. And so that's work that's ongoing at NRL. And so here are the takeaways. Nulling interferometry with LBTI is providing really sensitive probes of the circumstellar regions around nearby stars. Imaging interferometry with LBTI provides large field of view, 23-meter resolution, and masking observations with co-phased imaging can provide images that are robust to residual phase errors. And we're implementing a new fringe tracker upgrade that should give us an increase of about 5 magnitudes, taking us up to around 9th magnitude in K as our limiting magnitude for fringe tracking. So thanks for your attention.
Okay, thank you for the talk. Questions? Yep.
Hey, Jordan. Nice talk. This is Donny from K11. I have a question regarding the upgrade of the phase cam. Do you know what would be the improve in limiting magnitude with this upgrade? Do you know already?
Yeah, so we've run some rough numbers, and we think that we could get as good as K of around 10. So currently our limiting magnitude is around 4.7. But to be conservative, we're really targeting sort of a K of 9 as our limiting magnitude. And that's something that we think we should be able to get pretty easily. There's more than a factor of 100 reduction in the read noise going from the current implementation of FaceCam's picnic detector to this new Saphira array, and then we can also run a bit slower. So the picnic array right now really doesn't have a correct clocking table to be run 500 hertz.
Thank you.
Conrad, you have a question.
Yes, Conrad Tristram, ESO Chile. Can you remind me, I may have not paid attention, what's the maximum field of view you can do this interferometric imaging? And so you only need probably one object which is bright enough to actually do the fringe tracking. Is it then possible to look at much fainter objects and do interferometry on those, similar to what gravity off-axis is doing?
Yes, definitely. So right now our Elmercam detector subtends about 20 arc seconds on the sky. So it's a 20 arc second by 20 arc second field, which is somewhat similar to the isopistonic angle at Mount Graham. So we can do 20 arc second off axis fringe tracking. And yes, everything that once we do the adaptive optics and the fringe tracking on a bright source, anything within 20 arc seconds can be made to land on the detector.
Thanks.